Good afternoon, class. This experiment is experiment number 5. It's the 5th experiment. It's actually on page 6 of the lab manual, and it's called the Fletcher cart experiment. Now, there's a number of problems regarding this in chapter 4, and I will point those out after we do this little experiment. All it is a cart on a table like that. There's a string attached to the cart to a hanging weight like this, right down here. And when you let the thing go, what happens is the cart is pulled forward and it will accelerate. And the whole idea here is to determine the rate of acceleration of the cart. Now I'm going to do it real quick and we'll see what it comes out to be, and then we'll work out the problem and see how close we come out on this. All right, so you ready? Here we go. That was very simple. Turns out to be about 68 centimeters per second squared. 68 centimeters per second squared, about 0.68 meters per second squared. So that's hopefully what we'll get when we work the problem out. Now, since this lab is really unlikely that we're going to get the exact answer, but that's one of those things that happens in the case of the lab. So let me come over here now and we'll actually do the experiment. So we have, here's a hanging object. I'm going to call this number 2, because that's what I called in chapter 4 of the textbook. And what happens is this weight pulls down like that. And the weight of the object is mass times acceleration, m times g. Now it's being held back by the tension in the string. Now I'm going to refer to the tension in the string as F sub t. The tension string goes up, the weight goes down, but since the thing goes down, this is going to be bigger than that, and as a result it accelerates downward. Now the same string that holds this back is pulling this thing forward. So the forward force there. I'm going to put a dotted line around this, so I like to do that, which means we just isolate each object. And acting on the object on the table, we have its weight, and I'm going to call its weight m sub 1g. So this one is object 2, this is object number 1. And then in chapter 4, we talk about a normal force here, F sub n, the normal force, and that balances out the weight. Now there is another force here. It's called friction. And the friction between the cart and the table will hold it back. And so I'm going to F sub FR for friction. Now to solve the problem, we have to use Newton's second law of motion. The net force, unbalanced force, is equal to ma. We have two different objects to deal with. We have this one right here. This caused it to go down, so it's going to be m2g. The tension's holding it back, so it's minus the tension, and that's going to be equal to m2a. So let me say again. This weight right here pulls it down, the tension holds it back, and that's equal to that right there, okay? Now here, with this one, we have the tension pulling forward. Friction holds it back, and that's going to be equal to m1a. Now in our first lab experiment, we dealt with adding and subtracting algebra. So what we have is we have two simultaneous equations here. And we can add these two equations together. And when I do that, I'm going to end up with m2g minus F sub t, now plus F sub t, minus the frictional force, and that's equal to m2a plus m1a. And as you can see with this equation, let me go more slowly though. We have this one plus this one plus this one is equal to that one plus that one. So we have that. And then the tension was going to cancel out. That's the problem. So we end up with M2G minus the frictional force is equal to M2 plus M1 times A, because I can factor out the A from that side of the equation. Now, in order to finish this thing, we have to figure out what the frictional force is. So in the problem in the lab manual, it says, let's assume the coefficient of friction is 0.017. So the frictional force here is going to be equal to the coefficient of friction times the weight times the cosine of the angle. Right? The cosine of the angle is going to be 0 degrees, and the cosine of 0 degrees is equal to 1. So this is going to be equal to F sub FR will be equal to 0.017 times the mass of that cart, 0.525 kilograms, times 9.8 meters per second squared, times 1.0. So I'm going to get out my calculator now. We're going to solve what that is. All right? And hopefully I don't make the same mistakes I made the other day on this. It's at 0.017 times 0.525 times 9.8. And that comes out to be about 0.087. Sorry. My assistant says keep the razor close to me. I should have done that. 0.087. And this is going to be newtons. 0.087 newtons. Now going back over here, we said that this thing right here is about 0.05 times 9.8 meters per second squared meters per second squared minus 0.087. And the other side we have the mass of number 2, which is the hanging weight, that's 0.05, plus the mass of the cart, which was 0.525, times A. Now 0.05 times 9.8, that comes out to be 0.49. Minus 0.087 newtons. All right. And adding the other side, this comes out to be 0.575 kilograms times A. Now 0.49 minus 0.087, that comes out to be about 0.40. So net force is going to be equal to 0.40. And the other side we have 0.575. Kilograms times A. And so A is going to be about 0.40 newtons divided by 0.575 kilograms. Now get out my calculator. It says 0.40 divided by 0.575. And that comes out to be about 0.69 meters per second squared. Now when we worked it out over there, we got the answer to be experimental answer is about 0.67 meters per second squared. So they're off by about a couple of percent, but I'm not going to worry too much about that. You can work that out, you can figure out the percentage of error is, but it's probably about somewhere in the order of about 2% or so. Now at the end of this experiment though, and one of the things you have to do before you submit the experiment is actually do the review problem on the bottom of page 6. So the review problem is on page 6, the bottom, and that's part of the experiment, so you have to make sure you submit that as well. Now one last thing before we leave this experiment, what about the textbook? What problems are like this in the textbook? Now you're all registered for both the lab and the lecture class. So this will help you when you go to solve the problems in the textbook. So on page 4-18, and that's problem number 31. And then on page 4-21, there's two problems. It's number 41 or 42 and number 43. 42 and 43, and that's part of the lecture class work that you have to do. And that is the end of this experiment.